Hello everyone, my name is Jianjun He and I'm from Chongqing University. I'm honored to share my paper here. The paper I will share with you is duplicate backward port detection using dual-channel convolutional neural networks. For a software project, many people use it every day. In this process, users will inevitably encounter various bugs. Of course, the same bug may also be encountered by different users. When encountering a bug, users usually describe the bug and generate a bug report based on their understanding of the bug. Because different people have different understandings of the same thing, and different people may have different descriptions of the same phenomenon. This leads to the production of duplicate bug reports. We call bug reports that point to the same bug but are described in different natural languages are duplicate bug reports. Two bug reports pointing to different bugs are non-duplicate. In order to determine whether two bug reports are duplicate or non-duplicate, a common idea is to take two bug reports as input, then build a model and finally output the results. In order to use the bug reports described in natural language as the input of the determination model, our first step is to embed the words into word vectors. Here we use word2 vector as the word embedding model. In this way, we get two-dimensional matrices presenting bug reports. Such a two-dimensional matrix has only one channel, so we call it a single-channel matrix. Because the model receives two bug reports at a time, the next thing we have to solve is how to represent them. For a color image, it has three channels of RGB. When the three channels are output separately, the images of these three channels look very similar. For our duplicate bug reports, they mean the same thing. So we range them according to the channel. This two-channel matrix will be used as our input. After getting the input, we must choose a deep learning algorithm to build the model. First, our task is classification, and CNN has good performance in text classification, while RNN and LSTM perform well in generation. Second, our input now has two channels, and CNN has the ability to handle this multi-channel input. In this way, we call our model dual-channel convolutional neural networks and abbreviate it as DCCNN. This is an overall framework of our model. In the first convolution layer, we set up three different sizes of convolution kernels to extract the features of the dual-channel input. In order to simplify this figure, we have only shown the operation of one branch. The other two are similar because a row of the input represents a word vector. The width of the convolution kernel we set is equal to the width of the input. In this way, after a convolution, we get a number of column vectors. In order to perform the second convolution to extract higher dimensional features, we range these column vectors in columns. Three new sizes of convolution kernels are set to perform the second convolution. After this convolution, we use max pooling to reduce dimension and extract the most important features. Finally, we connect all the features from each branch to perform Fourier collection. We hope that the model will finally output a value between 0 and 1 to represent the probability that two bug reports are duplicate. Therefore, in the last fully collected layer, we use the sigmoid function to map the output between 0 and 1. We set the threshold as 0.5. If the output is greater than 0.5, we think that the two bug reports are duplicate. Otherwise, they are non-duplicate. Our datasets come from 3 projects: OpenOffice, NetBeans, and Eclipse. These data are provided by Laser. To create a larger dataset, we add up the data from these 3 projects and call it combined. Here are a few examples of the content in the datasets. A piece of data contains the ID of two bug reports and the relationship between them. We use the confusion matrix as a basis for calculating our evaluation matrix. Then we calculate accuracy, recall, precision, F1 scores, and AUC. Because the performance of baseline is already very good, when comparing the performance of our approach with the baselines, we calculate the normalized improvement, which indicates the room for improvement. Next, we answer several research questions to illustrate the performance of our proposed method. The first research question is that, compared with the state-of-the-art deep learning-based approaches, how effective is our DCCNN? This table shows the results of our approach and two baselines. As we can see, the performance of DCCNN exceeds two baselines in terms of all the evaluation metrics. Compared to baselines, our method does show better performance. We also want to know what factors lead to improved performance: TP, FP, TN, or FN. This table shows the specific TP, FP, TN, FN values of the 3 approaches. We can find that for positive samples and negative samples, the number of samples that DCCNN predicts correctly is increasing. This further proves that the performance of our approach is indeed excellent. The second research question is that, compared with single-channel convolutional neural networks based approach, how effective is our DCCNN? Our model is mainly composed of 2 parts. One is our dual-channel matrix, and the other is the CNN model. Therefore, we want to find out whether the dual-channel matrix works. We keep the structure of CNN unchanged and use it to extract features of 2 reports presented by single-channel matrices in a pair separately. We call this method SCCNN. This table shows the performance of SCNN and DCCNN. It can be seen that DCCNN performs better than SCCNN. Therefore, we can see that our dual-channel matrix presentation is useful. The third research question is that how effective is our approach in a cross-project detection setting? For a software project, especially a new software project, it may not have labeled data. In this part, when we test our approach on a target project, we use data from other projects to train a model. It is worth noting that when using OpenOffice as a training project, the experimental result of Lesbians is better. When using Lesbians as the training project, the evaluation result of OpenOffice achieves a better performance. By consulting relevant information, we find that OpenOffice and NetBeans are projects from the same organization. Projects developed by the same organization may have a lot of similarities. That's when a target project lacks labeled data, an alternative solution is to build cross-project model by learning from another similar project when using our approach. That's all. Do you have any questions?